Okay, imagine for a second a high-stakes pursuit. Not the kind with flashing lights and sirens, but a pure, elemental chase stripped down to its absolute core. Two bodies in motion moving through space and time on an inevitable collision course. We usually look at a chase as this chaotic event, right? Just a messy scramble of adrenaline and physical exertion. But if you strip away all that noise, what you're actually left with is an unavoidable mathematical truth. Welcome to our explainer. Today, we're going to track down a single, inescapable moment in time.
So here is the riddle that sets our whole universe in motion. Sarah and John are running a race. Now, Sarah is given a pretty generous 20-meter head start. John starts at the exact same moment from the very beginning of the track, but here's the catch. He is running faster. One runner has the advantage of distance, the other has the ultimate weapon of speed. The question isn't really whether John will catch Sarah. The question is exactly, precisely, down to the literal millisecond, when does this chase end?
Let's map out the raw physical realities of our two runners. Sarah begins exactly 20 meters ahead, and she is moving at a steady, relentless 4 meters every second. John starts way back at zero. He has zero lead, but his velocity is a blistering 6 meters per second. So we've got two distinct paths, two distinct speeds, and two lines that are absolutely destined to cross.
Section 1. The illusion of speed. Let's look at why our intuition completely fails us here.
Before we jump into the hard math, if we just track the first few moments of this race, you can see exactly why our brains struggle with this kind of thing. When we witness a chase out in the real world, our intuition is actually deeply flawed when it comes to calculating simultaneous rates of change. Think about it. At 0 seconds, before the clock even starts ticking, Sarah's totally dominating. She's at 20 meters, John is stuck at 0. After 1 second, Sarah pushes forward to 24 meters, while John only reaches 6. After 2 seconds, Sarah's at 28 meters, and John is at 12. If you're just standing there watching this happen, despite John's superior speed, these early seconds create this intense illusion that Sarah is mathematically untouchable. The gap is closing, sure, from 20 to 18 to 16, but because Sarah is continually moving forward, your brain perceives her lead as this persistent, almost permanent advantage. But you know, numbers, unlike our eyes, just don't lie.
Moving on to Section 2, Mechanics of the Catch. Time to translate this into math.
To find the actual truth, we need to translate this physical pursuit into a strict linear equation, and everything hinges on finding one hidden piece of information. We need to define our target variable. We'll call it x. Now, don't think of x as just some boring letter. Think of x as the exact hidden number of seconds that both runners exist in this chase before their paths physically collide. X is the culprit we have to track down to solve this mystery.
Let's actually translate that physical reality into mathematical language. Let's build Sarah's equation first. Her total distance is equal to her speed, which is 4 meters per second, multiplied by our hidden time x, plus that crucial 20-meter head start. So Sarah's reality is strictly defined as 4x plus 20. John's reality, on the other hand, is simpler, but it's way more aggressive. He starts at 0, so there's no head start to add. His total distance is purely his speed of 6 meters per second multiplied by the time x. John's reality is exactly 6x. Two runners, two completely independent realities.
Section 3. The universal intersection. This is where worlds collide.
Now, a chase only ends when those independent realities break down. So the really crucial point here is that the catch happens when John's total distance is precisely, down to the millimeter, identical to Sarah's total distance. To find out when this happens, we take John's reality, 6x, and we literally force it to equal Sarah's reality, 4x plus 20. Setting these distances equal to each other is the absolute mathematical equivalent of forcing the two runners to occupy the exact same physical space at the exact same time. The trap is set. Now we just have to spring it.
We have to isolate our unknown variable, x, essentially stripping away all the excess numbers. Step 1, we group the speeds together. We subtract Sarah's 4x from John's 6x. In the physical world, this actually represents John's relative speed. Step 2, we simplify. 6x minus 4x leaves us with 2x. This right here reveals the raw underlying physics of the whole chase. John is closing that 20-meter gap at a net rate of 2 meters every single second. So 2x equals 20. And finally, step 3, we divide the 20-meter gap by that 2 meter per second relative speed to totally isolate our unknown. X equals 20 divided by 2.
10. 10 seconds. That is the exact moment the illusion shatters. The two lines intersect and the chase is officially over.
Section 4. The proof. Let's verify reality.
But hey, in mathematics, a confession just isn't enough, right? We demand hard evidence. Let's plug our 10 seconds back into the original, independent realities to see if they actually align. For Sarah, 4 meters per second times 10 seconds is 40 meters, plus her 20-meter head start brings her to exactly 60 meters down the track. Okay, now for John. 6 meters per second times 10 seconds is exactly 60 meters. I mean, look at that absolute harmony. Both sides of the equation achieve perfect equilibrium at the 60-meter mark. The math is completely flawless. The physics check out. John catches Sarah exactly 60 meters from the starting line, precisely 10 seconds after the clock begins.
And finally, Section 5, Beyond the Numbers, taking math back into reality.
So why does any of this matter? Well, because the mechanics we literally just used to catch a runner are the exact same mathematical mechanics used to calculate orbital trajectories in astrophysics, or to write collision detection code in video game engines, and even to predict economic market intersections. Like this quote from our source material says, translating a word problem into a linear equation is about solving for a single inevitable reality. Abstract math isn't just a bunch of arbitrary rules made up by ancient scholars to torture high school students, it's the underlying geometry of everything around us. It is the code of the universe, allowing us to cut through all the chaotic noise of everyday life and pinpoint absolute truth.
So I'm going to leave you with this thought. If every physical interaction, every market trend, every single movement in the cosmos is really just a series of equations waiting to intersect, what hidden reality will you calculate next? The tools are right in front of you. Thank you so much for joining me for this explainer. And hey, if this sparked your curiosity, make sure you dive into our next explainer, where we'll continue to decode the fascinating architecture of our world. See you there.